Hi, welcome back. We are on our last video of the endocrine system. So this one has kind of three main parts. So I'm going to briefly talk about hormonal functions of other organs and tissues, focus on some of the key ones that I know we're going to see again in the future. Just one slide on hormonal interactions and one slide on the general adaptation syndrome. All right, so let's take a look at some of these other tissues. So I've just listed these pictorially. Okay. So we have in this first picture, we have, let's see, I'm going through the notes, the intestines, right? So this was our picture kind of like when we were talking about the pancreas. And I mentioned the duodenum. The duodenum releases a lot of hormones. We're going to see that in the digestive system. So I'm not going to go into the individual hormones, but again, just know the digestive system, the stomach does as well, intestines does, to release these hormones that help coordinate digestion and absorption of your nutrients. The kidneys, I'm going to talk a little bit more about the kidneys on some future slides, but the kidneys produce a couple hormones and an enzyme. So we produce the hormone calcitriol, the hormone erythropoietin, and the enzyme renin. So again, I'm going to talk a little bit more about that. The heart, right? The heart produces a couple hormones called natriuretic peptides, ANP and BNP. And again, we will talk more about those in the cardiovascular system after this, actually next. So chapters 19, 20, and 21 cover the cardiovascular system. So we'll see these hormones show up in more detail there. The thymus sits just underneath your thyroid, right? So here's your thyroid gland right here. Thymus kind of sits right over your heart. Thymus we'll see in the lymphatic system. It produces hormones that help to program your T cells. That's why they're called T cells, is because they go to the thymus for programming. And then we have the gonads, testes and ovaries. Testes produce testosterone, ovaries produce estrogen and progesterone. And like I mentioned earlier before, like with the adrenal cortex, I'm not going to spend, I don't need you to know all of the details of these hormones because we're going to see them more in chapter 28, the reproductive system. So we have enough hormones of the endocrine tissue that I can push off some of these others for in the body systems that we're going to spend more time. But I do want to talk more about what the kidney does because these hormones are going to come back so often that I need you to have a good grasp of these things that the kidney does. So one of the things that the kidney produces, and which we've seen before, is calcitriol. Okay? So calcitriol was produced by the vitamin D that was made in our tissues from exposure to UV light. So if you remember that way back in 231 in chapter 5, I think was our integumentary system. So sunlight turns cholesterol into cholecalciferol, is processed by our liver to produce an intermediate form that goes to our kidneys to produce calcitriol. Calcitriol works in concert with PTH to increase the absorption of calcium and phosphate, okay, helping with that blood calcium regulation. So those pair up. So that's one of the hormones in the kidney, calcitriol. We've seen that before, so we don't need to spend too much time on that. The biggies that I wanted to talk about is the hormone erythropoietin and the enzyme renin, which is huge. As you'll see, there's all this flow chart going on here. So we're going to start in homeostasis with normal blood volume and normal blood pressure. So, and this is all cardiovascular system stuff. So we'll get to this in more in depth in the next, the last third of the class. But let's say we have an imbalance in that we're losing blood volume and blood pressure, right? So falling blood volume and blood pressure is the trigger. So I guess this would be humoral because we're monitoring what's going on in the blood. So the kidney sees a lot of your blood all the time. So your whole blood volume is circulated through your kidneys like every 4 or 5 minutes. So it's a great monitoring site to see what's going on in your blood. So if you have lowering blood volume and blood pressure, one of the hormone, this EPO, is triggered to be released. It targets your bone marrow to increase red blood cell production, and that's going to increase your blood volume because the more red blood cells you have, the more blood you have. So that is one of the ways that we are going to increase our overall blood volume is by making more blood, by making more red blood cells. This decreased blood volume and blood pressure will also have a decrease in oxygen carrying capability, which is the red blood cells will also counteract that. The enzyme that is released, so renin is not a hormone, it is an enzyme, but this enzyme triggers a hormonal cascade. So in your blood, you have a precursor hormone called angiotensinogen. It's just floating around, it's inactive, it can't do anything. But in the presence of renin, angiotensinogen turns into angiotensin 1. And then it goes, and so now angiotensin 1 is circulating around, and it comes across capillaries in your lungs. And there's an enzyme called ACE, stands for angiotensin converting enzyme. This ACE enzyme that is found in the capillaries of your lungs converts angiotensin 1 to angiotensin 2. Right? Now, angiotensin 2 is the active form that can actually respond to this out of homeostasis drop in blood volume and blood pressure. So angiotensin 2 triggers a lot of things. 1, it makes you thirsty. 2, it triggers the release of ADH. So not only is ADH neurally stimulated by the hypothalamus, but it is also hormonally stimulated by angiotensin 2. And aldosterone is secreted. Okay. So remember, we talked about aldosterone, adrenal cortex, sodium and water regulation. It was humorally stimulated by watching the blood volume and sodium and potassium levels. It is also humorally stimulated by angiotensin 2, triggering the release. So if you remember, so this is going to increase water. ADH is going to increase water, antidiuretic, holds on to water, and increase water because of the water follows salt. So we have all three of these hormones triggered by angiotensin 2 is going to increase fluid intake and retention. So with increased red blood cells and increased fluid, which is basically the plasma part of blood, we have rising blood volume and blood pressure. We have more red blood cells to carry oxygen, and homeostasis is restored. Yay! Now, that's a lot of stuff. And I'm telling you this now because we are going to see this over and over and over and over again in the cardiovascular system, in the digestive system, in the urinary system, include electrolyte chapter. So we're going to see this quite a bit more. So I wanted you to get comfortable with these terms and this general pattern. So when we do see it again, you'll have a little bit of some familiarity with that. All right. So that is the focus of the kidneys that I wanted to spend some time on. The next is, this is information that's in the book. I made this table, so I don't know if there's a similar table in the text or if I just got it out of the words and the paragraphs, but I thought it would be an easy presentation of the information. So there's 4 ways that hormones can interact with each other for their target tissue or for the effect that's going to happen. So antagonistic is one of these interactions. So we've already seen a couple of examples of that. So their effect on their target tissue is opposite. So PTH and calcitonin. PTH increases blood calcium, calcitonin decreases it. Insulin decreases blood glucose, glucagon increases blood glucose. That's pretty straightforward, having an opposite reaction, antagonistic. Synergistic is these hormones do similar effects, but they are better when they happen together. So additive, the net result is greater than if each one was acting individually. So growth hormone and glucocorticoids would be synergistic. They're like helpers. And when they come together, they're more powerful together than they are apart. Permissive is one hormone is needed. You have to have one to give permission, basically, for the other one to show up. So epinephrine doesn't really work unless you have proper amounts of thyroid hormone. So even if you had plenty of epinephrine, if you are lacking thyroid hormone, you would also have a deficiency in the functionality of that epinephrine. So one has to be there to give permission for the other one to be able to do its job. And then last we have integrative, however you want to pronounce that, different but complementary results. So both calcitriol and PTH help to increase blood calcium levels, but they go about it slightly differently. So PTH can go and target your osteoclasts, but calcitriol can only go to your digestive viscera. So similar outcomes, but different ways of getting to that outcome, right? So just some vocabulary, hormonal interactions with some examples. All right, the last thing is what we call the general adaptation syndrome, or GAS, okay? It is your body's hormonal response to stress. So there's other ways that we can respond to stress, but we're just going to focus on the hormones and what they're doing here. This first box, we've already covered this. We just call this the alarm phase, but what is it? It is fight or flight or freeze or exercise. This is our sympathetic activation, dominated by epinephrine and norepinephrine. Norepinephrine at the synapses, epinephrine and norepinephrine hormonally from the adrenal medulla. All of this should look familiar. It's sympathetic activation, so we don't need to spend much time on that. It's not new. The second phase is resistance. This is if this stress lasts longer than normal, right? So if you're in a stressful situation of like almost getting into a car accident, you should be back to your parasympathetic in, a few minutes time. Or it could be even a stress of like a house fire or, something like that. But over time, you'll get back to normal. If that back to normal doesn't happen and you're continually in this long-term stress state, my brain goes to like, somebody stranded on a deserted island or somebody in a war-torn area or, famines and no food. So you're starving in a starving situation, to me, is what would be a good example of this resistance phase. So long-term metabolic adjustments, you can't maintain homeostasis because you're not eating food. So what is your body going to do to make you last as long as you can? So sympathetic activation cannot keep you in that fight or flight mode forever. So then we switch over to this resistance phase, and it is dominated primarily by your glucocorticoids, mineralocorticoids. Growth hormone a little bit helps with those, like growth hormone and glucocorticoids are kind of partners. So we're trying to maintain your energy reserves. So lipids are released. We're trying to hold on to your glucose, conservation of glucose. Burn your fats first, because neurons can only use glucose. Neurons cannot burn amino acids or fats. Glucagon helps to release your sugars, right? If you have stored sugars, we're going to release those because you're starving. You don't have any food. So let's try to store some glucose, but we still need some glucose. Let's kind of use our fats so we can store some of our glucose, but we can release some of our glucose. It's kind of like a battle between storing glucose and using glucose because we need glucose to survive, but if we have fats, we can use those as well. And then mineralocorticoids are conserving water and salts, and you lose potassium and hydrogen ions because that's just how aldosterone works, right? We hold on to sodium, but we have to kick out potassium. So these things might keep you alive a little bit longer. But if that is extending for too long, if that stress, you're on a deserted island with no food, or you're stranded in the desert with no food, or wherever you are with no food, or a war, you're a refugee and you have only contaminated water and disease and no regular supply of food, you're eventually going to die. This is called the exhaustion phase. You've used up all of your lipids. You don't have any more fat reserves. You have cumulative structural and functional damage to your organs. Your kidneys are going to start failing. Your pancreas is going to start failing. You are fatigued your adrenal cortex. You cannot produce any more glucocorticoids to help regulate your blood glucose levels. Your electrolyte balance is off. Your potassium, your sodium, which are really important for your neurons to function. And then you're just going to get organ failure and eventually die. And this happens for people who are in these long-term stressful environments. So for most people, they might be going through alarm phase every once in a while. There could be some people now, the world is in turmoil. There's lots of stuff going on that we might be seeing people in this resistance phase and unfortunately leading to the exhaustion phase if they don't get any remedy or humanitarian support. I know that's kind of a downer to end on our lecture. So just maybe go watch something funny to bring your spirits back up, or maybe give thanks for the things that you do have. All right, so that wraps up our chapter 18. That ends the second chapter that's going to be on the second lecture exam. So we have special senses and endocrine will be on the second lecture exam. And then after that, we'll jump into our next body system, which is the cardiovascular system with blood, heart, and blood vessels. All right, I will see you next time. Bye.